Okay, so let's get started. So last time I gave you this example. Okay, so where we have a car, an accelerating car, and then there's a pendulum set up inside the car, right? And then we have solved the problem. Okay, so just by using just a regular inertia frame, right? So and then we were able to find out the equation of motion for this small oscillation of the pendulum. Okay, so inside the car. Okay, and then we found that the oscillation frequency is given here. Okay, so which is different from just square root g divided by h, right? Okay, so now I would like to. Last time I didn't have enough time, but the last time I said that I would like to solve the same problem. Okay, so but using the accelerating frame, right? So this time we are in a frame that is actually accelerating with the car. Okay, right. So this. Okay. Actually, before doing that, so I want to make one more remark. Okay, just a revision for you is that if I want to find out the equation of motion, right? So last time I used just Newton's equation, right? So in fact, if you want to find out the same equation of motion here, right? So what you can do is that you can also set up the Lagrangian instead, right? So let me finish this remark first before I actually move on to the accelerating frame. Okay, so if I'm still considering the inertial frame. Okay, so and then I want to find the equation of motion, and by using Lagrangian. So how do I set up the Lagrangian this time? Right. So again, right. So you understand that we just have a KE minus PE, right? So but this time, when we set up the KE, right? So we need to be a bit more careful here, right? So we have to consider again the x component and the y component of the velocity of this pendulum, right? So the y component would be easy, right? So because it just so for the Vy, the y component, that would just be y dot, right? So but for the Vx for the pendulum, right? So that would be the derivative of this capital X minus small x. Right? And now, if you go ahead and take this, right? So this is d capital X dt minus x dot, right? So what is the capital X? The derivative of capital X with respect to time, right? So we know that the second derivative would be just a, right? So then you know that actually the first derivative would be some initial velocity plus at, right? So a is just a constant. Right? So that's why so this is capital X, okay? So that's why the dx dt, right? So it's just v naught plus at, okay, and then minus x dot. right? So therefore, the KE would be 1/2 m y dot square plus this whole thing square. Okay. So what about PE, right? So PE is just minus mgy, okay? Why is that minus? Again, I talked about it last time, right? So because this time I'm taking the negative, the downward direction as positive y. So that's why I have this minus sign in front of this mgy, right? So then the Lagrangian would be this term plus mgy, right? And then what you do next is the same thing, is that you want to express this x and y in terms of h and theta. Right, so that's what you're going to do. So that is right. So at the end, you will have a Lagrangian that is a function of theta and theta dot. Okay, and this time, so you also have this time dependence, explicit time dependence. Okay, but that's okay. You still write down this Lagrangian, right? So and then you do the Lagrange equation, right? So with respect to theta, then you should be able to find out the equation of motion, which looks like this one. Okay. Okay. So now let's get into the main the main theme of this chapter, right? So about the using the accelerating frame, and show you how it gives us some convenience in solving this problem. Okay. So now we are using the accelerating frame. So what does that mean? So that means that now I'm again going to, let me again draw the picture for the pendulum here. Like this, right? So we are in the accelerating frame, right? So that means that well, for the pendulum, for this mass here, right? So the gravitational force is pointing downward, which is this mg. So, but then we also have the fictitious force, right? So remember, so that would be to this side, right? Opposite to the direction of the acceleration. So that is m times capital A. Okay. Right. So now the picture you have is that you should not think of any acceleration anymore, right? So you just imagine that there's a static ceiling here, right? So with this pendulum setup, and then now, right? So the force acting on the pendulum would be, of course, is the vector sum of this mg and ma, right? So which is this one, right? So what is this force here? So this would be m square root a square plus g squared. Okay. So in other words, you just imagine that now this pendulum, this with a static setup, is in a effective gravitational force field, which is pointing this way, right? So with this magnitude, right? So if you imagine that, so if you have just a regular a setup that having the mg pointing down, right? So then this is what it will have, right? So and then the equilibrium position would just be vertical, right? So now in this case, right? So you expect that the equilibrium position would be something like this, right? It's not vertical anymore, right? So it would be along this direction here. Okay. Right. So let me erase this and then just draw again one force. Right, like this. And I'm going to just call this mg effective. Okay, let me call this G effective. And where G effective is, as I said, G squared plus A squared. So what is the difference of this case and this case? In the sense of the form of the equation of motion, they should be exactly the same, right? So because in this case, the swinging is something like this. And in this case, the swinging will be something like this. And in this case, the omega would be square root G divided by H. And in this case, the omega, without really thinking of anything new again, you can immediately write down that this omega is G effective divided by H, right? Because all you do here is you just change the direction of the gravitational field essentially, and change the magnitude also. So G effective is just what I have here, right? So that is just this. So here, right? So we have easily solved for the frequency, okay, by using the concept of this fictitious force. So and why is it easier to do the problem this way? So why is it easier to do it this way? Okay. So it's because previously when we do the inertial frame, we have to deal with this addition of velocities, and meaning the addition of accelerations. Okay, need to do the vector sum of the acceleration of the car and then the acceleration of the pendulum itself. Okay. So but then here we avoided that problem somehow, right? Instead, we just add the two forces together and form one so-called effective force. Yeah, I should have. Yeah, so this page is for you to write down this stuff here. Okay, so now let's see one more example. Actually, two more examples. Just to again have more practice on using this method of accelerating frame. Okay. So what I have here this time. So again, I have a car that is accelerating to the right at this capital A weight. And then here you can see that on top of the car, I have this setup here where I have a pivot which is free to rotate, and then I have this rod here, right? So that means that this rod here is like free to rotate like this, okay? So and the length of this rod is, so let me call this H instead of L, just to not to confuse with the Lagrangian. So the length of this rod is H, okay? So the question we are asking is actually quite similar to what we had in the last problem, okay? So well, in the pendulum, the setup is hanging down, but this rod is just hanging up. So the first question that I want to ask is that so now that this car is accelerating, and then now there's an angle between this rod and the horizontal level. So and the angle is being theta. Okay. So and what is the equilibrium value of this theta? Okay. So that is right. So this car is keep accelerating, and then the rod doesn't fall down, or it doesn't flip to the other side. So what is that so-called equilibrium value of theta? Okay. So let me call this theta naught. Okay. So again, we can solve the problem by using two different frame, right? So the inertia frame and also the accelerating frame. So let's do both. Again, let's do both. Okay. We can again do using the inertia frame first, maybe. Yeah, I'll just give you a couple minutes to try. Okay, so use the inertia frame first. And maybe here I'll use the accelerating frame. Okay, so let's try the inertia frame first. So first of all, again, if a diagram for us to label all the forces that we have, right? So of course, I'm just labeling this mg, right? So at the center of mass of the rod, and then there would be forces, there would be a force acting on this rod by the pivot. So that force should have both horizontal and vertical component, right? So let me just call this ny, and then this component to be nx. Okay. So now vertical component, consider vertical direction. So the if this is at the so-called equilibrium, okay. Well, the whole system, the rod is not in the equilibrium in the sense that this is actually accelerating to the right, right? So that's not the equilibrium, but well, first of all, we know that vertically, so vertically is an equilibrium, right? So if it's not falling down or flipping up, then the position of the center of mass will stay at the same vertical level, right? So therefore, at least in the vertical direction, there should not be any net force, right? So that is Ny is equals to mg, right? Okay, so now for the horizontal direction, right? So we know that the whole thing is accelerating, has a linear accelerating at A, right? So that means that the horizontal force, which is just Nx, has to be equals to ma, right? So just this. Okay. Okay, so I should have also indicated the angle in the diagram, but you know this is the angle, right? Okay, so now for it to be at the so-called equilibrium, so that means this is not, the rod is not rotating, right? So it's not rotating, so that means that we want to consider the torque acted on this rod. So one thing to be careful. So when we say that this is not a rotating, that means it's not, does not have any angular acceleration, I should say. Then that means that the torque acting on this rod is 0. Right? So, but what you need to be careful is that, so which reference point should we take? Right. So when I talk about the torque, right, so I need to take a pivot point and then do the R cross F. So should I be talking about the torque about this pivot point, or should we be talking about the torque about the center of mass? And then set that to 0, right? So if this is a real static problem, I'm not sure if you have learned this before. If it is a real static problem, and if you are considering the equilibrium, so there's no angular acceleration at all, then you should be able to get 0 no matter what reference point you pick when you calculate the torque, right? So when you deal with that static problem, right? So that is, if you take the torque about this point, you should get 0. If you take the torque about this point, you should also get 0, if it is really at equilibrium. Okay. However, that's not the case when the whole thing is accelerating. Okay. If the whole thing is accelerating, linearly accelerating, but without rotation, then you can only pick the point of the center of mass and conclude that the torque is 0. Right. So it's obvious in this case, if this whole thing is accelerating like this linearly, right? So if you take the torque about this point, so clearly you will get a non-zero torque, right? So because if you take the reference point here, then the only torque that you get is due to this mg, right? So, and that is a non-zero torque, right? So non-zero torque, but the whole thing, right? So we are considering the whole thing not being rotating, having any angular acceleration. So therefore, okay, so you can only take this point when you take the torque. So and why can and so forth? Why can't we take this point and get a 0 result? So this example gives you that it doesn't work. Okay, so but in general, how do I prove that or how do I prove why it is the case? Okay, so I might do it in the next chapter. Okay, so but here just remember the fact. Right, so when you deal with an accelerating object and you want to test whether it has an angular acceleration or not, then you will only have one choice, that is taking the torque about the center of mass. Okay, so if I take the torque about the center of mass, so what do I have? Right, so then this ny is one contribution, and then the nx would be the other contribution. Right. So the torque due to the ny right, so the torque due to the ny would be ny times this distance here, right? So this distance over here. So what is this distance? This is h divided by 2 half length of the rod times cosine theta, right? And then if I consider the other one, so the nx, so this one gives me a torque that makes this rotate clockwise, right? So but then nx gives me another torque that rotates anti-clockwise. So then that has to balance with, so if this is indeed not rotating, right? So then it has to balance by this nx times h divided by 2 sine theta naught. Okay. So with these three equations, so you'll be able to conclude that tangent theta naught what would be the tangent theta naught? So if I did sine theta divided by cosine theta, that would be equal to ny divided by nx. That would be g divided by a. Right, so this is essentially the same as what we had in the pendulum problem. Okay. Okay, so now let's use the accelerating frame. Okay. So again, right, so the idea is that now I just pretend that this system is not moving, right? So instead, right, so I have a fictitious force, right? So originally, so that's just the this gravitational force field, right? So like this. Now I have an additional effective force field, right? So to this direction, right? So due to the acceleration, right? So therefore, right? So effectively, there's a force field that looks like this, right? So the vector sum of the two force fields. And again, well, you know the direction, right? So you know the direction between the force field vector and the vertical line, right? So this theta. So that theta is exactly given by what we have here. Okay. right? So because it's like this. Oh, sorry, I don't want that to be theta. I want this to be theta, right? So like this. Okay, so for equilibrium, right? So the rod has to be parallel. The axis of the rod has to be parallel to the direction of the force field. Right, just like if you try to hold a pen, right? So if you try to put a pen on a table without falling down, right? So you need to put it exactly vertical up, right? So because the gravitational force field is exactly pointing down. Okay. So again, I conclude that this tangent theta is G divided by A. Okay. Okay, so in the part A, right? So in the part A, the two methods are kind of both simple enough. Okay, so now let's do part B, right? So what do we have in part B? So now I am at equilibrium position, and then now I displaced. I just give this rod a small kick, right? So that the rod now is a little bit tilted with respect to this position here, right? So that is, I make this rod a little bit like this. So I want to find out the behavior of this rod, right, as a function of time. So intuitively, if you look at this picture, you know what would happen, right? So because it's like you are trying to hold, have this pen vertically standing up on the table, but then now you just put it to the side a little bit, and then of course it will just fall down completely on the table, right? So that's qualitatively what is going on. Okay. So now again, I'm going to solve this problem, right? So in two ways. I think I want to just use the same figure. Okay, I'm just using the same figure here. So again, I'm going to consider the three equations, right? So vertical acceleration, horizontal acceleration, and then also the torque. So this time, so I'm not assuming this is at the equilibrium position anymore. So right, so then I don't have the theta naught. This is the theta. This theta can change as a function of time. Okay. So now that if I look at the vertical component of the force, so if theta changes as a function of time, so that means that the center of mass position of this watch changes as a function of time, right? So and then in both vertical and horizontal direction. Okay. So because as theta change, right? So this point will move like this, right? So the both horizontal and vertical position of the center of mass will change. Okay, so then vertical first, right? So the vertical force, I have this Ny minus mg, that is the net vertical force. That would be equals to m times the acceleration in the vertical direction. So first of all, let me write down the, again, just remind ourselves, right? So the if this is at the origin, right? So then the x position of the center of mass would be h divided by 2 cosine theta, and this center of mass y position would be h divided by 2 sine theta, right? So ny minus mg would be equal to m times d square dt square y dm, right? Right. So the total, the net vertical force would be equals to m times the acceleration of the center of mass of the system, and that is m d square dt square h divided by 2 sine theta. Okay. And what is this? This is m. Let me take the derivative one time first. So taking the derivative one time is h divided by 2 times cosine theta, theta dot. Right. So and then you need to take one more derivative, then you actually get two terms. Okay, so let me rearrange the equations. Just put ny as the subject here. Then you'll find that this is mh divided by 2. And then with two terms here. Like this. Okay, so now the horizontal direction, right? So just nx alone. So that would be m times the second derivative of the x position of the center of mass, right? Like this. And again, you need to just, well, put this into the XCM, and then just after some simplification, you should be able to get, oh, I'm sorry, not yet, missing something. So the total acceleration, okay, so the total acceleration is not just the derivative of the XCM. Actually, it has to add that with A, right? So, okay, yeah, I missed this term. Right, so you understand why. So because this XCM is measured with respect to this point O, right? So but this point O itself is accelerating to the right. So that's why I have to add this term with A. Okay, so then this is equals to the horizontal force. Okay. This. Okay, so if you just simplify, you will find that this nx given by ma plus like this. Okay. So finally, considering the torque acted on this rod, as I said, I can only pick the center of mass as the reference point. Okay. So the equation that I'm going to use is what? Is torque equals the moment of inertia times angular acceleration of the object, right? So the torque would be, I have already done it previously, right? It's nx times this minus ny times this that would be equals to the moment of inertia of the rod. I'm just calling ICM because of rotation about the center of mass times theta double dot. Okay. So I have three equations, right? So 1, 2, 3. And at the end, I want to find out the theta as a function of time, right? So then I want to eliminate nx and ny. So those are just simplifications of the equations. But if you actually do that, so let me just simply skip some of the steps. If you actually substitute the first two into the third equation, what you will get is the following. Okay. So some simplification has to be done by yourself. You'll get this. It just take a few steps, but and here you can see that on the right hand side, I multiply the whole thing by this square root factor and then divide the whole thing by the square root factor. It's just because I want to get to these two fractions. Okay. And what is this? So remember what we had previously is that what I said in the last slide is that tangent theta naught is what is tangent theta naught? Tangent theta naught is G divided by A. Right. And therefore, right, so that means that let me draw a triangle like this, right? So if this is theta naught, then this is G, this is A, and that is A squared plus G squared. Right, so therefore, right, so this thing is cosine theta naught, and this thing is sine theta naught, right? And therefore, this whole thing in the bracket is sine of theta minus theta naught. It's much simplified. Times m h divided by 2 times this square root factor here. Okay. So this equation, okay, so I cannot be solved analytically, but here at least you can see that there's a differential equation, right? So that relate this theta double dot with the function of theta. Right? And in fact, it looks pretty much like a pendulum equation, but without a minus sign in front. So let me use the other method, right? So the accelerating frame method, and do the same problem, and then the thing will becomes a bit more transparent. Okay. So if I if I use the accelerating frame, so what would I do, right? So as I said, it would actually be much easier. Okay, so now let me redraw this picture, right? So if I just draw this picture, the whole thing like vertically, right? So that would be like this. Okay. So and the only force that I need to worry about would be this one, and this I'll just call this mg effective, right? And that g effective, of course, is square root g squared plus a squared, like this. But as I said, you have this rod being held vertically up. If you just give a small kick, right? So you just fall down until it hit the table, like this. So you see how I get from this picture to this picture, right? So I just just rotate the whole setup a little bit, right? So such that now the effective gravitational field is again pointing down. So and in this case, I can actually just I'll just take the top, right? So as using this as the reference point this time, right? So because effectively the whole setup is not really accelerating on the car, right? So anymore, right? So that's the. So now if I take the talk about this point here, right? So then this time I call, let me call this angle here. So this angle, let me just call this angle phi. Okay. So in fact, phi, so it's just theta minus theta naught. Okay. Right. So this angle phi is just the angle displaced from the equilibrium position. So this is just theta minus theta naught. Okay. So this I, so now I'm going to again use the torque equals I times angular acceleration, right? So then this I, so this time the I is not the ICM, right? So again, it is I at this point, using this point as the rotation axis. I'm just going to call this I. So I times phi double dot right? So it's equal to the mg effective times h divided by 2 sine phi. So if I use this, right? So accelerating frame, that's it, right? So not many steps, right? So and then I have this. So and this is the same as this equation here. Right? Can you see why? Because so this phi double dot is theta double dot minus theta naught double dot. Right? So that's why the left hand side is just theta double dot. And then on the right hand side, I have phi, which is theta minus theta naught. And here on the right hand side, I also have the theta minus theta naught. Okay. And then here I have the G effective. Right, so let me just right? So put it over here, right? So now this, as I said, this phi double dot is just theta double dot, right? And then this sine phi is just this sine theta minus theta naught. And then this G effective, right? So just this square root G square plus A square. And then this I on the left hand side, this I is the I about 0.0. I about 0.0 would be equals to this parallel axis theorem, right? So the ICM plus the m times the distance between the center of mass and the O, which is x over h divided by 2 squared, right? So this whole thing is I. Okay. So then I hope you're convinced that the two cases, in the two methods, we arrive at the same result. Okay. So now, as I said, right? So if you just look at this equation here, right? So if you have a minus sign in front, that would be a pendulum problem, right? So if I have a minus sign in front, that means that you could imagine that means the whole setup is like upside down, or you can say that this G is pointing up, right? So then obviously that would be a pendulum motion. So, but now this is pointing down, so this rod won't do a pendulum motion like this, right? So instead it will just fall right down like this. Okay. So now I have one last exercise here. So I think for this one, I won't spend the time again to do both methods. Okay, so I'll just do the easier method with the accelerating frame. Okay, so after we complete this problem, we'll take a break. So what is this problem about? So you can see that again, I have a truck here, so a top view of the truck. So initially, this door, the back door of this truck is open like this, right? So it's supposed to be, if it's closed, this whole thing should be do a 180-degree turn, right? So that is closed on this. So it's fully open now. And then now the truck is accelerating at a constant rate, again, capital A. So what happened is that this door will like swing like this. Okay. And then as it swings, right? So the angular velocity of the swinging motion will increase as a function of time. Okay, so we want to find out as the door swings to this position at that moment. So what is the angular velocity of the door? Okay. So if you don't think about the accelerating frame, if you just think of the inertial frame, so first of all, do you understand why the door will swing like this? So because there's a pivot here, right? So initially nothing is moving, but as this truck starts accelerating, so then there will be a force. Right, so at this point, right? So there will be a force acting on this door by the truck, right? So through this pivot here, right? So and that would produce a torque on this door, and that's why it will swing. So in fact, it is doing rotation, both rotation and translation. Again, you could imagine this door is doing both rotation and translation. Right, so because the whole truck is moving right? So and then this door also, right? So the actually, right? So then that's why it swings like this, right? So it's not, well, it won't be a pure a rotation or pure translation. So if you actually look at the inertial frame. Okay. So but now, right? So let's just focus on the accelerating frame, right? So if I'm at the accelerating frame, right? So this time I'm going to just forget about the acceleration. Instead, I will get an effective force field pointing back like this. Right. So then you could again just imagine that this door is under the influence of an effective gravitational field, something like that. Right. So, but of course, instead of having, it's not small g, right? So, but it's a. Okay. So the acceleration due to this effective gravity is a, right? So not g. So then, now that would be pretty easy to solve, right? So you could actually think of using conservation of energy, right? So because as I said, this whole thing is just under the effective gravitational field, right? So that initially the rod is like this. So then the center of mass is right over here. So as it has swings by 90 degrees, the center of mass position is here, right? So therefore, the change in height, well, quote unquote height, is given by this one, right? So I'm just going to call this. So this is again. Let me just say that this is h, right? So and then this change in the so-called height would be h divided by 2. So therefore, right? So the loss of quote unquote PE, gravitational PE, of this door would be mg. Oh, actually, the parameters are defined all here. Okay, so here I should, but that doesn't matter really. So here, let me call this W. Okay. So this is W. Okay. W divided by 2. So the loss of PE is mg times W divided by 2. And that would be converted to the kinetic energy of this door, right? So the gain of PE, KE, what would that be? So initially there is no KE, right? So and then as it swing by 90 degrees, so I have this omega here. So remember, so that would be just a pure rotation about this point, okay, about this endpoint. So what is the KE? Is 1/2 times I moment of inertia, right? So about this point times omega squared. So therefore, right, so 1/2 I omega squared is just mg times W divided by 2. So if you really want to solve it, so I is given by 1/2 m W squared, actually, right? I'm sorry, in this drum is 1/3. So then omega actually is 3a divided by w. Okay. So that's it. Right. So again, you could imagine that, although I'm not going to do it, if you really want to solve the same result using the inertial frame, that would be less convenient. Okay. Okay, so let's take a break. Okay, we'll take a 10 minutes break. Come back at 10:45, and then we will start the next part of the chapter, which is the rotating frame. Okay. Okay, so now we are getting into the part 2 of this chapter. Okay, so and I would say this part of the chapter is more difficult than the previous part. So because in the previous part of the chapter, so the fictitious force we have is very intuitive and easy to find, right? So if you have the reference frame to be accelerating to the left, then your fictitious force would be to the right, right? Just exactly in the opposite direction. Okay. So in this part, we are not going to consider a linear accelerating frame anymore. Instead, I'm going to consider a so-called a rotating reference frame or rotating coordinate systems. Okay. So I want you to look at this picture over here. Just don't look at the equations yet, but just look at this picture here. So you can see that again, I have two set of coordinate systems. So the black one, which is given by the x, y, z, and then the red one, which is labeled by this x prime, y prime, z prime. So what happened is that just imagine that the black one is not rotating and not moving. So in both systems, so they share the common origin here. Okay, so that the origin itself is not accelerating. Okay, so this point is always fixed. However, what happened is that the red one is the rotating coordinate system. So that means that the x and the y axis are moving. So, and then you can imagine that the tips of the arrows are moving along this circle here. Okay, and in this case, I'm just assuming that the rotation axis is the z-axis, so that's why the z prime axis is not moving as a function of time. So then I think this is easy to imagine, right? So what a rotating coordinate system looks like, just like this. Okay. Okay, so now let's get back over here. So before I talk about rotating coordinate systems, so first let's do a review on just rotating vector. So the rotation of a vector. Okay, so here you can see that I have this diagram. So the xyz itself is a fixed coordinate system, and then I have this red vector. So just for simplicity, just imagine this red vector is just lying on the xy plane, and then this red vector is rotated by some amount by this angular displacement, this delta theta, and then I get to this blue vector, which is the r prime. Okay. So I hope this is clear. And now, so this picture here, it's just redrawing this whole thing, but just showing you the xy plane. Okay, so this is the top view of this thing. Okay. So delta theta, right? So you might remember this notation. The delta theta, this notation was used in chapter 2, when I was talking about rotational symmetry and virtual angular displacement, right? So you might still remember that. But here, so I just want you to remind you that, so now I'm not really talking about the virtual displacement anymore. Okay, so well, I'm still using the same kind of notation, this delta, but just bear in mind, not virtual angular rotation, angular displacement anymore, because you might still remember that the virtual displacement concept, right? So it happens, is a displacement that happens at no time, right? So no time was involved. Okay, so but now, okay, so you have to have this concept that, so now I'm actually rotating this vector, red vector, in real time, right? So it takes some time, so for this red vector to get to this blue vector, so within some time delta t, so the rotation is given by this delta theta. This happened within a small time interval delta t. Okay, so now, and you can also see that the delta theta. So the reason why I use delta is, again, you might guess, is that I'm considering the so-called infinitesimal amount, right? So it's a small amount. Okay. So, but anyway, so let's get started by writing down some equations. So originally, right, so the R vector. Okay, so let me also say that let's say the length of the vector is capital R, and that is fixed, right? So then this R vector, what is it? Is R cosine theta x hat plus R sine theta y hat, right? So now what about the blue one? So after rotation, this R prime, which is given by R cosine theta plus delta theta x hat plus R sine theta plus delta theta y hat, right? Okay, so now I want to know, what I want to know is the difference. Okay, so between the two vectors, that is, I want to know what I call the delta R, which is defined by R prime minus R. Okay, so, and geometrically, that would be this vector over here. Okay, so, or this vector. So is the vector, this small vector, connecting the head of the two R vectors, right? And you can see that, right? So these three vectors together form a very narrow triangle, right? So I think you have seen something like this before. But okay, so anyway, so now I want to find out the expression for this delta R. So, but one thing here is that, as I said, I'm saying that this delta theta is very small, right? So then if I'm going to just make approximations, then that would just becomes like this, right? So the just using the Taylor expansion. So cosine theta plus delta theta is approximately equal to cosine theta minus delta theta sine theta. And similarly, this sine term is just approximately equal to sine theta plus delta theta cosine theta. Okay, like this. Okay, so therefore, if I do R prime minus R, that would give me, right? So just this blue line minus this red line over here. Then that would be R delta theta times minus sine theta hat plus cosine theta y hat. Okay. Okay, so now you can actually see, okay, either from the formula or from the picture, is that this delta R is basically it is perpendicular to R. Okay, you look at this picture, you can see that. Or if you look at this formula, right? So if you take the dot product between delta R and R, you would get this minus sine theta cosine theta plus cosine theta sine theta. That's 0. Right. Right. So this delta R is perpendicular to R. And also you can see that from the formula, the magnitude of this delta R is given by R big R times delta theta. Right. And again, geometrically, you can also see why, right? So because if you just imagine that this is small enough, right? So then you have this small enough so such that this small triangle just behave like a small circular arc here. Then this delta R divided by big R is just given by delta theta. Okay. So in fact, delta R can also be expressed as a cross product of C cross R. Okay. You can try your right hand grid rule, right? So C cross R get you this direction. And then this magnitude agrees with this magnitude here. Okay, so well, in general, I want to consider a vector that might not be lying on the XY plane, right? So I might want to consider a vector look something like this, but also rotate about the z-axis. Okay. So just like this. Okay. So I think this picture is also included in, as I said, it is in the chapter of chapter 2 when I talk about the rotational symmetry and the virtual angular displacement. So the same figure here. Okay. So in general, so if you have the vector that is not necessarily lying along the XY plane, right? So like this. So if I again draw the so this time my coordinate system still looks like this, right? And I'm considering this R vector, so being rotated. Okay, so again about the z-axis by a small angle delta theta, then I get to this vector. Okay. And again, so by this, just looking at this geometry here, so you'll be able to conclude that this delta R, this change in R, given by this delta theta cross R. Okay. So this delta theta, okay, so if I go back to here, so basically I'm defining this delta theta vector as delta theta times z hat. Okay. So that's how I define it. So then this is also can be written as this. Okay. So that is the delta theta vector. So the meaning of delta theta vector is that, so first of all, the magnitude of the delta theta vector is just the delta theta, right? Just the amount of the angular displacement. And the direction of the delta theta vector gives you the rotation axis, right? So in this case, it's just the z-axis. Okay. So that's how I define the delta theta vector. Okay. So now, as I said, right? So this displacement happens within some time delta t. Okay. So delta t. So now if I want to find delta r delta t, right? So all I need to do is to divide both sides by delta t, like this. Okay. So then this is what I have here. So dr dt is given by d theta dt cross r. And so if you consider the vector r is the position vector of a particle, right? So then this dr dt, of course, is the velocity v. And this d theta dt, I am going to define it as the so-called omega. That's the angular velocity. So the right-hand side is omega cross r. Okay. So in principle, when I talk about the vector here, so when I say that this is r, of course, you imagine that this is the position vector of a particle, but of course, it can be other vectors. It does not have to be a position vector. It can be other vectors, but anyway, this is here, I'm just focused on using r. Okay. Okay, so this v equals omega cross r. I believe this is something that you have learned before, right? So at least I believe that you have used the scalar version of this, right? So you might use this a lot, v equals omega r. Okay, so without worrying about the vector nature. Okay, but in general, so this is how we have the relation here. So v equals omega cross r. Okay. So and as I said, right, so for other vectors, a, so I can just write this dA dt equals omega cross a. But of course here you need to be careful is that this a vector, okay, so I'm assuming that the time dependence of this a vector is only due to the rotation itself. Okay, so here I'm assuming that this r also, I'm assuming that the magnitude, right? So the magnitude of the r is not changing over time, as you see from my argument here. Okay, so the only time dependence is due to the rotation itself. Then I can write it this way. Okay, so here is a remark, but you don't really need to worry about it right now. Okay, so but I'll just say a few words. Right, so now I have used a vector, right? So to represent an infinitesimal rotation. Right. So, however, we have not yet proven that infinitesimal rotations indeed follow the rules of vector operations. So what does it mean? So I mean that, so if you define this something as a vector, so that means that you have to follow the following rules, right? So that is, you can do addition like this. So that means that you can do addition like this, right? So, and also the order of the additions should not matter, right? So it should give you the same result, right? If omega is indeed vector, then this one should be true, okay? But we have not proven that this one is indeed true yet. Okay. So because if you think about a large rotation, so not infinitesimal rotation, if you rotated something about one axis first, and then rotate the same thing about the other axis. So let's say you rotate something about the x-axis by some degree, and then rotate the same thing about the y-axis by another degree. Right. So would it be the same as rotating the same object, but this time first about the y-axis first, and then rotate that about x-axis? Okay. So the order of the rotations for large angle or for finite rotations, that's actually matters. Actually give you different results. Okay. But for infinitesimal rotations, okay, so that is okay. But I won't say anything further at this point. So, but because we don't need to worry about it in this chapter. Okay, so the omega vector will always be just one fixed vector. Okay, so we are not adding two rotation vectors together in this chapter. Okay, so then don't worry about it for now. Okay. Okay, so now we really want to talk about the rotations of coordinate system. So just now I talked about rotation of a vector, right? So as I just introduced, right? So we are thinking of making a vector to rotate relative to the coordinate axis. Okay. So this time we are not going to rotate the vectors. We're going to rotate the coordinate systems. And what does that mean? So that means that we are taking the same vectors, right? So but as the coordinate system is rotating, right? So then we express the same vectors again, right? So using a different basis, right? So because you know what is our basis is the x hat, y hat, z hat, right? So when you express a vector, you express in terms of x hat, y hat, z hat. So as the coordinate system is rotating, then that means that the basis keep changing, right? Change to x hat prime, y hat prime, z hat prime. So you need to express the same vector in terms of this x hat prime, y hat prime, z hat prime. Okay, so that's what you need to do. So that is now to describe the rotations of a coordinate system. So basically what we are going to do is to describe the rotation of the basis vectors, right? So now, right, so as I already said, for a fixed coordinate system, x hat, y hat, z hat are the basis vector. So now for the rotating coordinate systems, in this case, to make it easier to follow, so suppose I say that the rotation of the coordinate systems, okay, so it's about the z-axis, okay, and the angular velocity given by this omega, so omega z hat. Okay. So now if I want to express the the new basis vectors due to the rotation. So I can make use of the results that we got, right? So it's this d dt, a vector dt is equals to omega cross that vector. Okay. So therefore, the rate of change of the basis vector, like this dx hat prime dt, dy hat prime dt, and dz hat prime dt, are given by omega cross themselves. Okay. So, and now you have this omega cross x prime. So actually, this I should write x hat, y hat, z hat here. Right. So what is this omega cross x hat prime? So omega is omega z hat, right? So that means it's omega times z hat cross x hat prime. And z hat cross x hat prime, by using again the right hand grid rule, would be given by this y hat prime. Because although the axes are rotating, but still the three axes are always perpendicular to each other. Right? But similarly, right, so this dy hat prime dt is given by minus omega x hat prime. Okay. And this one is 0, okay, because it will just give you this z hat cross z hat prime. They are two parallel vectors. Okay. And so be careful, right? So that now this x hat prime and y hat prime, they are all function of time, right? So then this dx hat prime dt is omega y hat prime, and this one y hat prime itself is also time dependent, right? So, because as you can see here, dy hat prime dt is going back to the omega minus omega x hat prime. Okay. So if the rotation axis is not along the z-axis, but is somewhere maybe here, so you can still have these three relations. Okay. But of course, then in that case, this omega cross x hat prime won't be simply given by omega times y hat prime. Right. So you really need to give me what omega is. Right. So you need to give me the direction of this n hat vector. So it depends on our problem. Okay. Okay. So just now, so here essentially nothing is new here compared to what we had previously. Right, so that one is a rotation of any vector, a position vector. So here we are doing the rotations of the basis vectors themselves, and that would represent the rotation of the coordinate system. Okay, so now what I want to do is to so express a vector. So in the rotating coordinate system. Okay. So a vector A. So this blue one. And again, so you can think of A is the position vector or particle, or it can be other physical quantity. Okay. So now A itself, okay, imagine the A vector itself is a function of time. Okay. So initially, so previously, when I'm talking about the stuff here, the R vector. Okay, so I would just tell you that the time dependence of the R vector is purely due to the rotation of due to the rotation. But here, the A vector can be arbitrary. Okay, right. So just forget about the coordinate system or whatever. Just imagine that the A vector can. Okay, so the A vector itself. So at some time, the A vector can be like this, and some later time it can become maybe longer like this. Okay, so and some later time it can go even longer like this. Okay, so the A vector is doing its own thing. Okay, so and we don't worry about what it is doing. Okay, so the A vector itself can also be rotating or it can be not rotating. Okay, so just A is a function of time. Okay. So, but anyway, at any particular time, so using the black coordinate system, the fixed one, A can be written like this. Okay, so the AX x hat plus AY y hat plus AZ z hat. Okay, and this AX, AY, and AZ themselves can be function of time. Okay, so now if I take the time derivative, that is easy. Just taking the derivative term by terms, right? So in this case, I don't need to worry about the derivatives of the basis vector themselves, because for the black coordinate systems, the basis vectors are just constants. Okay, so but now, this is the part that we need to be careful. Okay, so I'll just finish this slide, and we'll continue next time. Okay. So now I'm going to express the same vector, right? So I'm not trying to rotate this A vector. I'm expressing this A vector, but using the red coordinate system, which is the rotating frame. Okay. So then now the A is expressed like this. Okay. So what I'm writing here is AX prime, X hat prime plus AY prime, Y hat prime plus AZ prime, Z hat prime. Okay. So you understand the difference between X hat and X hat prime and so on. And also note that AX itself is not equals to AX prime. Okay. So the coefficients are different, the basis vectors are different. But at the end, this whole thing is equals to this whole thing. Right? So because both of them are referring to the same vector, just expressed in different coordinate system. Okay, so individually, AX not equals to AX prime. Okay, X not equals to X prime, and so on. Okay. Okay, so now if I take the time derivatives, this time we need to be very careful, because we understand that now the basis vector themselves are also function of time due to the rotation omega. Right, so that's why when I take the time derivatives, I need to, for the first term, I need to use product rule. For the second term, I also need to use the product rule. Also for the third term, I need to use the product rule. So that at the end, I will have 6 terms in total. And then these 6 terms, I will be putting them in 2 groups. Right, so the first group is the groups where the time derivatives are taken for the coefficients. And then the second group is that the time derivatives are taken for the basis vectors. Okay. And this first group, I will denote this by dA dt with the subscript rotate. It means that this is the rate of change of this A vector viewed by an observer in the rotating frame. Okay. So if you imagine that you stand on the rotating frame and rotate in the same manner, right? So according to you, you will think that all these basis, this red basis vector are not changing as a function of time, right? Because you are rotating at the same manner. You will only, but if the vector is indeed changing, right? So you will still be able to notice that, right? So by all these three derivatives, okay. But truly, the dAdt is not just what the rotating observer sees. Okay, so there's another group of terms here that need to be taken care of. Then we'll continue next time. Okay, so to finish deriving the expression of this time derivative for the vector in the rotating system, rotating coordinate.